This question is on capacitors. You have two capacitors charged, you connect them in parallel and you have to calculate how much is the energy lost. So I read this question. A capacitor of capacitance C1 is charged to a potential V1. C1 charged to a potential V1, while another capacitor of capacitance C2 is charged to a potential difference V2. The capacitors are now disconnected from their respective charging batteries and connected in parallel to each other. Find the total energy stored in the two capacitors before they are connected. Find the total energy stored in the parallel combination of the two capacitors. Explain the reason for the difference of energy in parallel combination in comparison to the total energy before they are connected. Okay? So, there is a capacitor, capacitance C1 charged by a battery, say to a potential difference V1. Another capacitor of capacitance C2 connected to battery and its potential is raised to V2. Now what is done? The capacitors are disconnected and they are connected in parallel. This plate would have become positive, this plate would have become positive, the other thing of course negative. So these two capacitors are now connected in parallel. They will have a common potential difference V. First thing we have to find out is what is the energy initially, that is before they are connected together, both the capacitors. That's quite simple. Initial energy, I just use this symbol EI to indicate initial energy. Energy of this plus energy of this, total initial energy. Half C1 V1 square plus half C2 V2 square. Also you will have to find out what is the energy of this system. For that it's better if you know the expression for common potential difference. So we will see how to find common PD that we can use in calculating the final energy. One thing you should understand, whenever these capacitors are connected in parallel, charge remains same, charge is conserved. We can say charge is conserved. We are going to prove that energy is not conserved. Okay? So what is the total charge here? C1 V1 plus C2 V2, total initial charge. Formula for charge is CV, or capacitance is defined as, formula for capacitance Q by V. Capacitance is defined as the ratio of charge to potential difference between the plates. So Q is CV. So charge in this plus charge in this, that should be equal to charge in this combination. Charge in this combination is, potential is common. Now you have to use effective capacitance. Again you will have to be very careful whenever the capacitors are connected in parallel. The effective capacitance, if you want to calculate, use 1 by C is equal to 1 by C1 plus 1 by C2, where C is the effective capacitance. If they are connected in parallel, C is equal to C1 plus C2. Okay? Yeah. Now your aim is to find this common PDV. So V is equal to C1 V1 plus C2 V2 by C1 plus C2. Let's keep this ready, we will use in this. Now what is the total final energy in the sense after they are connected in parallel? This is the total initial energy. Total final energy will be, okay, E final half effective capacitance C1 plus C2 common PD's square V square, that is C1 V1 plus C2 V2 by C1 plus C2 square. You can simplify this, half C1 plus C2 square here in the denominator. So this will become C1 plus C2 in the denominator. So C1 V1 plus C2 V2 square divide by C1 plus C2. This is final energy, E final. Okay. Now we have to find out whether there is any loss in energy or whether there is any gain in energy or there is no change in energy. We have to find out. For that, what do? We evaluate initial energy minus final energy using these two expressions and see what happens to the final expression when we evaluate this. So E initial half C1 V1 square plus half C2 V2 square, E initial. I think I can remove this diagram. Then E final is this, so minus half C1 V1 plus C2 V2 the whole square divide by C1 plus C2. Simplify. Take C1 plus C2 as LCM. So half into C1 plus C2 V1 square plus half C2 into C1 plus C2 V2 square minus half we have to use this C1 V1 plus C2 V2 square, okay, whole divided by C1 plus C2. Okay, C1 V1 plus C2 V2 square. I'll write properly. C1 V1 plus C2 V2 square. Okay. Now you will just to take the numerator alone and simplify of this. So this numerator alone, half C1 square V1 square plus half C1 C2 V1 square plus C2 square V2 square half C2 into C2, here V2 square is there, plus half C1 C2 V2 square minus half, you expand it using A plus B whole square formula, C1 square V1 square plus C2 square V2 square plus 2 C1 C2 V1 V2 is equal to half C1 square V1 square plus half C1 C2 V1 square plus half C2 square V2 square. Okay, I'm sorry. please correct it. C2 square V2 square plus half C1 C2 V2 square minus half C1 square V1 square minus half C2 square V2 square minus half here, 2 there. So minus C1 C2 V1 V2. Only the numerator alone I am expanding. Okay. Half C1 square V1 square minus half C1 square V1 square, half C2 square V2 square minus half C2 square V2 square. Collect the remaining things, equal to half C1 C2. Here it is C1, please change it. Half C1 C2 bring outside, V1 square, C1 C2 outside, so plus V2 square. C1 C2 outside, but there has been half taken out, so minus 2 V1 V2. When you simplify the remaining things in the expression, this can be written as half C1 C2, this will be V1 minus V2 the whole square. But you see, this is only numerator. So energy loss means you have to divide it by C1 plus C2. So the loss in energy or the change in energy, let's say change in energy, and interpret, is half C1 C2 by C1 plus C2 V1 minus V2 the whole square. So initial energy minus final energy is this. Right side is a positive quantity or a negative quantity? Right side. Positive quantity or negative quantity? So positive quantity. Why? Because this cannot be negative. Capacitances are not negative. The values are not negative. But there is a square here. So whether V1 greater than V2 or V2 greater than V1, this is going to be positive all the time. This is positive. This is also positive. So the product positive. So initial energy minus final energy is positive, means initial energy is more than the final energy. That means there is a loss in energy. So how do you explain this loss in energy? See, this is comparable to inelastic collision in mechanics. In inelastic collision of say two bodies, momentum is conserved, but kinetic energy not conserved. You might have studied in your 11th standard. Kinetic energy not conserved. Similarly here, charge is conserved, but the energy stored in the capacitors not conserved. That means what happens to the missing energy? That is converted into heat because of the charge sharing. Charges have to go from one capacitor to the other. Heat may be produced, there may be spark. So in all the other forms like this, the energy may be lost. Understood it? Thank you.